Welcome back to Physics 191. I'm Gerard Blanchard. Last time we left off with our full set of kinematic equations. The kinematic equations are the equations that we use in a kinematic situation. And a kinematic situation is one that deals with motion. That is, acceleration, velocity or changes in velocity, changes in position, and time. To deal with these kinematic situations, we have four equations for you to choose from. And you can see them here. What's different between these four equations is what's not in them. You choose which equation to use based on what you don't know and what you don't need to know. Sometimes you don't know the acceleration. You don't need to know the acceleration. You don't know the final velocity, and you don't need to know the final velocity. You don't know the change in position, and you don't need to know the change in position. Or you don't know the change in time, and you don't need to know the change in time. So you'll have to analyze the situation and pick the best starting equation based on what you don't know and what you don't need to know. Let's practice. Here's a situation. A car is speeding up and has an instantaneous speed of 1.0 meters per second when a stopwatch reads 10 seconds. It has a constant acceleration of 2.0 meters per second squared. What is the speed of the car when the stopwatch reads 12 seconds? Now remember how to approach this. First, we're going to model the situation, which means you draw a diagram. You draw the initial and the final situation. You list all of your knowns and unknowns. And then you determine what it is that you don't know and don't need to know and pick the proper starting equation. And you also have to identify this as a kinematic situation, which it is. So please try. Let's draw our diagram. We start off with a car. There's our car initially. We know that the initial time, which I'll write as t initial, is 10.0 seconds. And its initial velocity is 1.0 meters per second. And we're going to say that the car is moving in the x direction, so we'll make that our x-axis. And we'll call that Vx initial is 1.0 meters per second. Finally, the car is over here somewhere. It's moved over there. We know that t final is 12.0 seconds. Vx final, we don't know. We can also call our initial position, and call that x initial. We can set that to 0. We can call our initial position to be 0 meters. And x final, we don't know. We do know that the car is accelerating in the x direction with an acceleration of 2.0 meters per second squared. Now, so far, we've diagrammed the situation. We've listed all of our knowns and our unknowns. And since we have a change in position, a change in velocity, and a change in time, we know that this is a kinematic situation. A kinematic situation. And we have to choose the equation based on what we don't know and what we don't need to know. Well, we don't know Vx final, and we don't know x final. What we're asked for is Vx final. So we need to know Vx final. We don't need to know x final. So we would choose our kinematic equation that doesn't have x final in it, or that doesn't have change in position in it. And that equation is Ax is equal to Vx final minus Vx initial over T final minus T initial. That one should be familiar. That was our first equation that we've worked with a few times now. Now we have completely modeled this situation. Now it's just a matter of making our equation specific to this situation and solving for whatever it is we need to know. Well, let's see. Ax, we know, is 2. And once again, I'll leave off my units so as to not clutter things. 2.0 meters per second squared is equal to Vx final minus Vx initial, which we know is 1.0 meters per second, and then divide by T final of 12.0 seconds minus T initial of 10.0 seconds. Now we solve for V final. 12 minus 10 is 2, so we have 2.0 is equal to Vx final minus 1.0 over 2.0. We'll have to multiply both sides by 2.0. And then 2.0 over 2.0 is 1, which I don't have to write since we're multiplying by it. And so that gives us 4.0 is equal to Vx final minus 1.0. We'll add 1.0 to both sides. And so finally we see that 5.0 is equal to Vx final. What are our units? Well, we're in basic metric units, so we know that our basic metric units of speed or velocity are meters per second. So Vx final is equal to 5.0 meters per second, and we've answered the question that was asked of us. If we wanted to, we could also answer the question of what is x final. We weren't asked, but we could also have found an equation with x final in it without Vx final and answered that question as well. But we weren't asked, so we won't do that this time. Let's try another exercise. A cheetah can accelerate from rest to 24 meters per second in 2.0 seconds. Assuming the acceleration is constant over the time interval, what is the distance traveled by the cheetah in these 2 seconds? You approach this the way that we approach every other situation in here. You draw a diagram, list your knowns and unknowns, identify the type of situation that we're dealing with, and then we know it's going to be a kinematic situation, so you'll have to choose the kinematic situation that based on what you don't know and don't need to know in this situation. So give this one a try. Okay, well, we start as we always do by drawing our diagram. We have our cheetah, we have our square cheetah. Everything's a square. And the cheetah starts off initially, T initial, which we can call 0 seconds. T initial is 0 seconds. We can choose to start our stopwatch wherever we want. It says he accelerates from rest. So Vx initial is 0 meters per second. He's initially at rest. And we don't know where he is. We weren't told where he is, so we can choose to make his initial position the origin of our x-axis. We can choose where to start measuring from, and we can choose x initial to be 0 meters. We're free to choose where we start our stopwatch, and we're free to choose where we measure distance from, where the origin of our x-axis is. Unless we're told specifically, something specific. But generally, we're free to choose those. The cheetah accelerates, but we don't know what his acceleration is. We're just told that he does accelerate. So AX is an unknown. And we're told that finally, T final, Vx final, and X final. The final situation is 2 seconds later. We're told that he accelerates from rest to 24 meters per second in 2 seconds. So that means that T final is 2 seconds. Vx final is 24 meters per second. And X final, we don't know. We're not told what X final is. And in fact, X final is what we're looking for. So we've drawn our diagram. We've listed our knowns and our unknowns. Now it's time to identify the situation. We have a change in position, a change in velocity, a change in time. All of these indicate that we're dealing with a kinematic situation. A kinematic situation. And we have to choose our starting equation. And we remember that we choose our starting equation based on what we don't know and don't need to know. Well, we don't know x final, but we need to know x final. We don't know the acceleration in the x direction, and we don't need to know that. So we're going to choose our kinematic equation that doesn't have acceleration in it. And that equation is that the change in position divided by the change in time, or x final minus x initial over t final minus t initial is equal to the average velocity, or Vx final plus Vx initial over 2. So change in position over change in time equals average velocity. Now we have completely modeled this situation. We've diagrammed it, we've listed our knowns and unknowns, which means that we've gotten all the information we can out of it. We've identified the type of situation, and we've picked our starting equation. Now it's just a matter of making this equation specific to this situation and working through it. X final, we don't know. We do know x initial is 0. Divide by the change in time, t final is 2 seconds, minus t initial, which is 0. That's equal to Vx final, which is 24 meters per second, plus Vx initial, which is 0, divided by 2. And we have an equation, there's only one unknown in it, so all we have to do is solve for x final. Well, let's get rid of all these zeros, plus zeros and minus zeros, and we have x final divided by 2 equals 24 divided by 2. And I can multiply both sides by 2. Cancels out my 2 there and my 2 there. And we see that x final is equal to 24. And 24 what? 24 meters, because position in basic metric units is measured in meters. So we've answered the question. The cheetah, in the time that he accelerates from 0 to 24 meters per second in 2 seconds, travels 24 meters. So this is an example of a situation in which we didn't know acceleration, and we didn't need to know acceleration, so we started with this kinematic equation. Let's try another example. A train of mass 55,200 kilograms is traveling along a straight level track at 26.8 meters per second, which is 60 miles per hour. Suddenly, the engineer sees a truck stalled on the tracks 184 meters ahead. If the maximum possible braking force has magnitude of 84 kilonewtons, can the train be stopped in time? Let's think about that. We know what the first thing is that we have to do. We have to draw a diagram. And the real question is, what distance does it take for the train to stop? So when you draw your diagram, draw the train in its initial position, draw it in its final position, list all the knowns and unknowns that you know, and you'll also, in this case, have to draw in the forces that are affecting the motion of the train. This is going to be a case in which we're going to have to combine our kinematic equations with Newton's second law. So there's a lot here, but if we follow the procedures, then we can answer this question. So go ahead and get started. Draw your diagram, list all your knowns and unknowns, identify your equations that you need, and let's see what you can do. Okay, well, we'll start, as always, by drawing our diagram. Here's our train. Initially, here's our train finally. And we know that we have to be concerned with time, velocity initial, initial position, final time, final velocity, final position. All of that is the same. And we know that the train is moving in the x direction. The acceleration in the x direction, we don't know. What do we know? What can we identify from the statement? Well, we know that the train has a mass of 55,200 kilograms, and it's traveling at 26.8 meters per second. That's going to be Vx initial. We can call our initial time 0, and we can also call our initial position 0. So we have the initial situation. The final time, we don't know. the final velocity. Well, what is our final situation? The final situation is where the train comes to rest. So the final velocity is going to be 0 meters per second. And our final position, we also don't know. That's in fact what we're looking for. We're told one more thing. We're told that there's a braking force of 84 kilonewtons. So if the train is moving in this direction, if the train is moving to the right, then the braking force would be applied in the opposite direction. And we'll just write F is equal to 84 kilonewtons. And we have to convert that to newtons. And our conversion factor is going to be 1,000 newtons is the same as 1 kilonewton, so that the force is 84,000 newtons. Now there are also forces in the vertical direction. In the y direction, there's going to be weight downward and the normal force of the track upward. But since we're only dealing with motion in the x direction, we don't really need those right now. We could in other situations, but in order not to clutter up my diagram, I'm not going to draw in those y forces because they're not going to affect the motion of the train in the x direction. Okay, at this point we have drawn in all of our knowns and our unknowns. So we've completely analyzed the situation to get all of our information that we can possibly get out of it. We have to pick our equations now. Well, we have motion, we have a change in time, a change in velocity, a change in position. So we know that this is going to be a kinematic situation. And let's see what that does for us. Well, we need to pick a kinematic equation. What do we not know, and what do we not need to know? Well, we're not asked how much time does it take for the train to come to rest. So we don't know time. We don't need to know time. So let's try our equation that doesn't have time in it. And that would be Vx final squared minus Vx initial squared is equal to 2ax times x final minus x initial. Let's see what that will do for us. Vx final we know is 0 minus Vx initial of 26.8 meters per second squared, actually I didn't need to write in my units, is equal to 2 times the acceleration in the x direction times x final minus x initial, which is 0 meters. Well, that has two unknowns in it. It has x final and it has ax. What can we do about that? Well, we know that we can use Newton's second law to relate the mass of the train to the force on the train and the acceleration. And so since the train is changing its velocity, this is also a non-equilibrium situation. So we also have x non-equilibrium. And in that case, the acceleration in the x direction is equal to the total force in the x direction divided by the mass of the train. And as long as you realize that there's a mass, that you know the mass, you know the forces, you know that you can get the acceleration from Newton's second law, so that even though we didn't know acceleration, we knew that we could find it. So let's see what that gives us. AX is equal to the total force in the x direction. Well, what forces do we have acting in the x direction? There's only one, and that is the braking force. And that is 84,000 newtons divided by the mass of the train, which is 55,200 kilograms. And that means that we can calculate AX. Oh, actually, I made one mistake there. The force is 84,000 newtons, but it's pointed in the negative x direction. So we have to be sure to have our negative sign to indicate that the force is pointed in the negative x direction. And so we have AX is equal to, let's see, negative 84,000 divided by 55,200 is 1.52, and we know what our units must be. If this is acceleration, then that would be 1.52 meters per second. And now we can take that and put it into this equation, which will then leave us with only one unknown, and we can solve it. So I have minus 26.8 squared equals 2. And I'm sorry, I made the same mistake again. I didn't carry down my negative sign. Equals 2 times negative 1.52 meters per second squared for the acceleration times x final, or negative 26.8 squared, and I'm going to divide both sides by 2 times negative 1.52 equals x final. And let's see where the train stops. Negative 26.8 squared divided by 2 times negative 1.52 equals 236 meters. So 236 meters is the final position of the train. So we know where the train comes to rest. It comes to rest 236 meters from where it started. Unfortunately, the truck was 184 meters from where the train started. So unfortunately, the train didn't stop before it hit the truck. There's a couple things here you can learn from my mistakes. Be careful about the negative signs. The force was in the negative x direction, so I had to put a negative sign there, and which meant that our acceleration is negative. And that was important because as the train moved from here to here, it was slowing down, or it was accelerating in the negative x direction. And so if we didn't keep our negative sign, our equations wouldn't have worked out. So be careful with those negative signs. And also, the other lesson to learn is that if you're given the forces on an object and its mass, then you know that you can get the acceleration for your kinematic equation from Newton's second law. Let's look at another example. Grant Hill jumps 1.3 meters straight up into the air to slam dunk a basketball in the net, with what speed did he leave the floor? This is another kinematic situation. You have a change in position, a change in speed. Well, actually, we'll have to infer the change in speed. If he's jumping 1.3 meters straight up, that means that he was initially moving upwards. And if he only moved 1.3 meters up, then at the top of his jump, he comes to rest for just a moment. So we know that at the top of his jump, his velocity will be 0. So we do have a change in position, we do have a change in velocity. We're not told time or acceleration, but remember that you can get his acceleration by considering the forces. You're not told his mass, but it's possible if you think about it. So what I would like you to do is to diagram the situation, draw in the forces, pick your kinematic equation. Remember to think about Newton's second law, and see what you can do with this exercise. Okay, let's draw our diagram. Here's Grant Hill. We have T initial, and we know that he's going to be moving in Y. So we'll have T initial, Y initial, Vy initial. We'll have T final, Y final, Vy final. And we know that he's going to be accelerating, AY. And let's see what we know about this. T initial, we can call that 0. 0 seconds. We can choose to start time anywhere we want to. Y initial, well, we'll call the floor 0 meters, so we'll say that he starts from 0 meters. Vy initial, we don't know. And in fact, that's what we're asked to find. What is Vy initial? T final, we don't know. Y final, we're told, is 1.3 meters. And Vy final is something that we had to infer from the exercise statement. And that is, if he jumps 1.3 meters up, and that's as high as he gets, then at that point, when he's at the top, he's not moving up anymore. He's right at the instant between moving up and down. So at the very top of his jump, at the very top of his 1.3 meter jump, we know that Vy final is 0 meters per second. For just a moment, he's in between moving up and moving down, which means that he's not moving at all. So Vy final is 0 meters per second. And AY, we don't know. Let's think about the forces on Grant Hill. We know that once he leaves the floor, he's being pulled down with his weight. Gravity is the only thing pulling him down. And we know that his weight is equal to his mass times g, downwards. We don't know his mass. We'll just write that as m. Mass is another unknown. We do know g, though. Well, let's see what we can do with that. Let's start off with Newton's second law. We know that this is a non-equilibrium situation. He starts off moving upward. but his velocity changes, so he's not moving at constant speed. So let's start off with Newton's second law, or the fact that we have a y non-equilibrium situation. From Newton's second law, we know that his acceleration in the y direction is equal to the total force in the y direction divided by his mass. Let's think about what that does for us. Well, acceleration in the y direction is equal to the forces in the y direction. What forces do we have on Grant Hill? Well, the only force that we have is his weight, and let me draw in my axes. This is y. Weight is pointed in the negative y direction, so that would be minus mg, and that's the only force acting on him. The only force acting on him is weight, or gravity. It's in the negative y direction. So we divide that by his mass. And look what happens here. The mass divided by the mass gives us 1. And so the acceleration would be negative g times 1, or just simply negative g. So we have ay is equal to negative g, or the acceleration in the y direction is equal to minus 9.80. And let's think about the units here. We know that g has units of newtons per kilogram, but that's also equal to a newton is a kilogram meter per second squared, and then we divide by a kilogram. A newton per kilogram is the same thing as a meter per second squared, so the units for acceleration are, in fact, what we knew that they had to be since we were dealing with acceleration. And so the acceleration is minus 9.8 meters per second squared. So now we know his acceleration. And in fact, it didn't matter what his mass is. We didn't know his mass. It didn't matter. It could have been any mass, which also means that this could have been any object, not just Grant Hill in particular. Because when the only force acting on the object is weight, then the mass will cancel out and we'll always have an acceleration of minus 9.8 meters per second squared in the y direction, that is. Okay, well, let's go back up. Now that we know that the acceleration in the y direction is minus 9.80, let's think about what kinematic equation we need. What do we not know and not need to know? We don't know time. So, for our kinematic equation, we would pick the equation without time, and that is Vx final squared minus Vx initial squared is not x, we're dealing in y now. So Vy final is equal to Vy final squared minus Vy initial squared is equal to 2ay times y final minus y initial. Vy final squared is 0. Minus Vy initial squared, Vy initial squared, that's what we're looking for, equals 2ay, which we now know is minus 9.80 times y final of 1.3 meters minus 0, or Vy initial is equal to negative 2 times negative 9.80 times 1.3, and we have to take the square root. So I multiplied both sides by negative 1, and then I took the square root of both sides to get Vy initial. And that tells us that Vy initial is equal to the square root of negative 2 times negative 9.80 times 1.3, and that is 5 meters per second, or 5, and we know that the units have to be meters per second. So once again, as always, remember to always approach these questions with our procedure. You draw a diagram, you analyze the situation, which means that you get all of the information that you can possibly get, either from what is explicitly stated or what is implied, and then you identify the type of situation. We knew we had a kinematic situation, but we also could realize that we needed Grant-Hill's acceleration, so we had to also use our non-equilibrium equation, or Newton's second law, to get Grant-Hill's acceleration. And what we discovered is that even though we didn't know his mass, we could figure out his acceleration because the only force acting on him was weight. And when the only force acting on an object is weight, then in Newton's second law, mass cancels out to give us an acceleration that is always equal to g in the negative y direction, or an acceleration of negative 9.8 meters per second squared. This is our first exposure to a situation that we call free fall. Free fall is a special circumstance for kinematics where the only force acting on an object is gravity. And in that case, we're going to know that the acceleration is negative 9.8 meters per second squared in the y direction. Next time we're going to deal with more free fall situations. And until then, think physics.